The following program is brought to you by Caltech.
And welcome everybody, both on behalf of the Keck Institute for Space Studies and on behalf of the Planetary Society. We at the Planetary Society are very happy. This is not the first event we've done with the Keck Institute, but it's really a great relationship, and we're very proud that so many people came. How many people are members of the Planetary Society? Just take it. Okay, who you did not put up your hand, please go outside. We'll take care of that later. In 1950, I was in school. I won't tell you what school, but I was in school. I was just a kid. And there was less than 50 asteroids known. Today, we're discovering 3,000 a month. There's literally tens and tens and hundreds of thousands of them known. Millions of them will be known. And we are finding out so much about and changing our view of the solar system, the world, and our neighborhood. This is our neighborhood, the Near-Earth Asteroids, and tremendous population changing the way we think about things. We're in the middle of a workshop here, and this is why this event is being done, on the idea of moving an asteroid. Now, some people have heard about these ideas about moving an asteroid away from Earth. It's a little different study this week. We're studying about moving an asteroid a little closer to Earth. And the idea is that we can now even think about these things and do these things is tremendously exciting because asteroids are turning out to be an incredibly interesting and important subject. The thing that motivates us is that there's now a great deal of interest in sending humans to an asteroid. Not as the end goal for human exploration, but these are natural stepping stones to move out into the solar system. And the idea that we have these in our neighborhood, the Near-Earth Asteroids, and it's a place where astronauts can go set new distance records, new time of flight records, going beyond the moon, which is all we've achieved thus far, is now, I think, exciting a lot of people. It's a new goal for NASA. The president has gotten behind it, and we hope that we're making strides to start a process that will actually see astronauts take those first steps. But even the first steps are just to get beyond the moon is perhaps an empty space, just to go out there before we even reach a near-Earth asteroid. So a few people have gotten the idea, maybe we should move an asteroid a little closer to Earth and make it a natural target for human exploration. We don't know yet if this is a good idea. We don't know if it's a safe idea. We don't know yet what's required to actually implement this idea. But the Keck Institute is devoted to these kinds of studies to think these things through and at least find out what's required and then think about how it might be accomplished. I want to introduce Tom Prince. He's the director of the Keck Institute here and a professor here at Caltech. And we appreciate the fact that you have this broad look on getting these studies going, and I hope we're coming up with something. But even in the idea of humans going to asteroids, that's only one aspect of the interest in asteroids. Just scientifically studying them, getting up close and examining them, looking at the composition. There are different types of asteroids. We'll hear more about that. Motivates us to teaches us things about the origin and evolution of the solar system. Asteroids could be a source of resources. There's metal asteroids, there's carbonaceous asteroids. We'll hear more about that this evening. These could be places where we could actually extract materials to do further things in space, to make them not just stepping stones to step on, but stepping stones to actually build things on and build things from as we move out into space. And then there's the danger of near-Earth asteroids. I'm sure you've all heard, some have impacted the Earth. I heard about one that landed in Arizona and caused a crater out there near Flagstaff. Asteroids have influenced the history of Earth greatly. And we know that, again, they will influence the history of Earth in the future. And so the idea of perhaps that someday we might have to defend ourselves against an asteroid or divert an asteroid that's coming toward Earth is receiving a great deal of attention. So whether you're interested in the exploitation of space and doing new things, or whether the protection of Earth, whether the scientific studies, whether human expansion into the solar system, asteroids are becoming not just objects of curiosity, as they were in the 1950s, but objects of great importance to the future understanding of our place in space and the future of human exploration in space. With that, we have a terrific panel, and I'm going to turn it over to them. It's really an honor to have all four of these people here, and I'll introduce them one by one. The first is Rusty Schweickart. Rusty is an Apollo astronaut, had flown in the Apollo program. That's what he's most famous for, but he's also famous here in California for serving on Jerry Brown's Commission on Energy. He graduated MIT from the Aeronautics and Astronautics Department, and he's been a leader in formation of an organization called the B612 Foundation, and a leader in the Association of Space Explorers, which is the association of all those people who have flown in space, astronauts and cosmonauts. And they have taken upon themselves, under Rusty's leadership, in a large part, to study the whole question of planetary defense and how we might have to learn more about asteroids and then even perhaps defend ourselves against them in the future. Great pleasure to introduce Rusty Schweickart.
Eureka. See, I did it right. Well, thank you. I'm going to have 10 minutes here before we introduce succeeding speakers, so this will be pretty quick. Lou gave the sort of broad picture that asteroids have a number of facets which are of interest for varying reasons. The one I've focused on for the last 10 years has been planetary, what we euphemistically call planetary defense. And by that we mean fundamentally what to do when we know or believe that an asteroid is about to hit the Earth. There are fundamentally two things that you do. One is you run. We call that civil defense in the civilized world, but basically it's get the hell out of the way, let it hit and not get you. If we know about it enough in advance, we can take proactive measures to deflect it. We go up with our space technology, with spacecraft, and we actually change its orbit so that it will not hit the Earth when it was going to 10 or 15 years in the future. So this is, when you step back and think about it, this is an incredible presumption that we can do this. I mean, if you think for a minute, stand back and think about life on Earth and the fact that the Earth has been around for the 4.5 billion years of the existence of the solar system, and asteroid impacts on the Earth have occurred all through that time period. And by the way, not all back there in the beginning and tailing off to nothing, but rather a sort of pulse way back then. But from 3.9 billion years ago or so up until now, it's relatively constant as best we know. And so this is not something in the past. This is a continuing process that we're involved in, and we're not generally aware of it because our lifetimes are 100 years, and these things hit with, let's say, 300-year or larger or longer frequency. So it's not something which we see like a hurricane or whatever, but this is a natural hazard in much the same way that big storms and floods and other things, earthquakes, are natural hazards. The big difference is that because of our ability to look into space with telescopes and to spot these, discover these asteroids, the ones that cross the orbit of the Earth, we call those Near-Earth Asteroids. once we discover them, we can plot a trajectory on them, an orbit, and we understand orbits pretty damn well, and we can therefore predict ahead up to 100 years and say, if this asteroid's orbit has an intersection with the orbit of the Earth, and let me just go ahead and start doing this. We're going to do a really quick fundamentals here. But if I take the orbit of the Earth here, if I'm looking down on the solar system with the sun up there out the roof, and here's the Earth's path around the sun, here's a path of a near-Earth object, okay, and that they cross at this point. But now you're in three-dimensional space, so this is not really an intersection unless in the third dimension, in and out of the plane of the screen here, it's also an intersection. So where you have a three-dimensional intersection like that, it's simply a matter of time before the Earth, the green dot there, is in that intersection, and an asteroid happens to be this asteroid happens to be going through that intersection at the same time. That's what an impact is, and the whole problem with that we're confronted with then is to, if we know this impact is coming by predicting orbital behavior, we can then take action ahead of time to make sure that, in fact, the asteroid is not in the intersection as the Earth passes through. Now, what we do with that, to do that, we either make the asteroid, we change its orbit so that it arrives too soon in the intersection and it's already passed through the intersection before the Earth gets there, or we slow it down, we make it arrive late so that the Earth gets through the intersection before the asteroid arrives. And that's the whole process of planetary defense. Now, I just point out for those of you who are into relative motion that the velocity of the Earth is like this at the intersection. The velocity of the NEO is angled up. The relative motion, that is, if you're driving along this freeway and another car is driving along this freeway, you don't look in your rearview mirror to see if somebody's going to run into you. You look out the side to see if this car is going to collide with you in the intersection, right? So this action, this is the direction, the apparent direction from which the asteroid arrives. And I'm going to ask you in a moment to ride on that asteroid as it heads for the intersection there. Okay, the other thing on this graph is this white line. While we know very accurately when the Earth is in that intersection, we do not know very accurately when the asteroid is going to be in the intersection. And if you think of this white line being made up of a million little white dots, okay, the real asteroid can be any one of those virtual million white dots, and we don't know which one it is. We can limit it, and in fact, as we get more and more tracking, that white line gets shorter and shorter, but we don't really know exactly where it is. And that is the reason why, unfortunately, we're going to have to make a decision to protect the Earth and spend $300 million or more, let's say $1 billion, to go up and protect the Earth when we think that the probability of impact is, let's say, 1 in 10 or 1 in 50 or 1 in 100. So this is a very difficult political decision. But in any event, the asteroid is sort of a blur here. We don't know exactly where it is, and that's an important fact to realize. I'm going to forget those technical things. Now, what happens when an asteroid goes past the Earth? Here is, again, looking down on the Earth, but now we're traveling along with the Earth. And here's an asteroid that comes along. Its name is Apophis. You might have read about it. On Friday the 13th of April, 2029, it's going to come whistling past the Earth. And this is the actual geometry. Looking down on it, it's going to come in from basically opposite the direction of the sun. It'll go behind the Earth. The Earth, of course, is moving down and to the right. And in fact, the asteroid, remember, is moving down and to the right also. But the relative motion, it comes in, it'll pass behind the Earth. And because it's this close to the Earth when it goes by, the Earth is going to bend its trajectory. It's going to actually pull it forward, and it's a significant change in the orbit. The asteroid here is coming in at about 5.86 kilometers per second. It's going to go out at the same velocity relative to the Earth because nothing slows it down. There's no loss of energy. So effectively, the Earth, if you complete that parallelogram, the Earth gives that asteroid a kick in the pants of 2.83 kilometers per second. And that's a heck of a change in velocity. So the end result is that when it came in, the asteroid had a period, that is, the period of its orbit around the Sun is less than a year, 323 and a half days. But when it goes out, the asteroid period now, because it got this kick in the pants, it now has a period of 426 days, longer than a year. So there's a dramatic change in the asteroid because of this close approach to the Earth. Now, that's all well and good because it didn't hit the Earth. But the irony is, of course, you realize if you know anything about orbital mechanics, which you may or may not, that if it were closer to the Earth, it would get even a bigger kick in the pants, and it would have an even longer period, a bigger orbit around the Sun. Or if it passed a little further away, it would have a less of a change. And the danger in a close pass like this is that it passes just at the right distance, where, in fact, it's a multiple of the Earth period around the Sun, a multiple of 1 year. So, in fact, Apophis is going to come very close to what we call a keyhole, which could cause it to come back and hit the Earth 7 years after this date, which, again, will be April the 13th, but it will be Sunday, 2036, and that's Easter Sunday. So you can look forward to that. Okay? Now, I don't want to go into this too much, but let me just say these keyholes that I talked about are very important. This is looking at the uncertainty of where if you're riding the asteroid toward the Earth, this is where you might pass by. That's essentially now a horizontal view of that white line that you saw in the first slide. And if you pass in the middle of it, you get a kick in the pants, which gives you a 426-day period around. Well, lo and behold, 426 days means that you go around the Sun as an asteroid 6 times, the Earth has gone around 7 times, and you come back together and hit. So each of these so-called keyholes, this one is 7 years for the Earth and 6 years for the asteroid going around, 6 orbits of the asteroid going around, and they impact. Here's another one which is 8-7. Each of these is a different keyhole. And in other words, whenever an asteroid goes by the Earth, close, there are a whole series of these very small but very real potential disaster zones. If it goes through very small regions, these little windows in space as it goes by the Earth, then we can have an impact later. And what we need to do then is being able to project that forward. We say, okay, let's go up. I'm going to bypass a lot of that. We're going to go up and we're going to say, okay, let's change its arrival time at that intersection so that we're not going to go through that keyhole. And since these keyholes are very, very small regions in space, we don't have to make a big change in the asteroid's orbit 10 years ahead of time. And so we can run into it the way we did with Deep Impact. That's one method. It's a brute force method, and it's not very precise. And one of the things you want to do is have a precision end result. So while you may use a blunt instrument like an axe to get the primary job done, the fine work you want to do with a scalpel, gravity tractor being an example, where using gravity, just hovering in front of an asteroid with a little bitty spacecraft, you very slowly and weakly pull it toward you. And so you can get a very precise change in the orbit for the final part of a deflection using a technology of this kind. I point out that both of these technologies are currently available. In order to protect the Earth from most asteroid impacts, we do not have to develop new technology. We do need to prove this technology by demonstrating it, but it exists already. So we have the capability, physically, technically, to protect the Earth from asteroid impacts. The implication of that, I want you to think about for a moment. We have been hit millions of times in the 4.5 billion years, and life would not exist without the impacts of asteroids and comets over the history of the solar system. But once life emerged, then asteroid impacts have from time to time wiped out large percentages of life. And since we're now on the top of the totem pole, we care about that. Generally speaking. Not everybody, let me say. But generally speaking, we do. And what I'm going to tell you is that with our technology combined with our brains, which have generated machines, at the level we are now in our evolutionary state of life here on this planet, in this corner of the solar system, we are now able to very slightly and subtly reshape the solar system in order to enhance human survival. And that's the fundamental reason that we're here now in this workshop. But that's a reality which says we human beings have the arrogance and the capability to say we're going to stop a process which has gone on for 4.5 billion years. Now, I'm going to close simply by saying an outrageous statement. If there is a community of intelligent life out in the universe, big if, it will have already, those intelligent beings will have already conquered this challenge. Our entrance exam to that community of intelligent life is to pass this test. Thank you.
Rusty should have noted that the dinosaurs failed that test, and would that they only had a Rusty Schweickart among them to have pointed that out. Our next speaker is also an astronaut, and so we're very honored to have Tom Jones join us. Tom is a shuttle astronaut, being younger than Rusty. Shuttle astronaut who played an integral part in the building of the space station, delivering the U.S. module there. In addition, he's a scientist, has been studying the subject of asteroids ever since his college days. He's an author of a book called Skywalking about his experiences in space, as well as a book about planetary science called Planetology. He's a frequent lecturer. He's an experienced Air Force pilot. He's done a whole host of activities, and we're delighted that he is an advisor to the Planetary Society and is helping to both advance the human and robotic exploration of the solar system. Tom Jones.
Well, thank you, Lou, and hello, everybody, tonight. It's good to be with you all. I remember that Carl Sagan wrote in his book, Pale Blue Dot, that unless a society learns to move around small bodies in their own solar systems, then they're condemned to extinction. So Rusty's message is very well taken. And I think where I'd like to build on Rusty's presentation is to talk about how humans can not only anticipate and then prevent collisions here on Earth, but also move out into the solar system and take advantage of the benefits that asteroids offer us in terms of exploration and resources and so on. So I'm going to focus my next 10 minutes on the potential for human exploration, how it fits into how we get to other places even beyond the asteroids in the future. And like Rusty, I'm a member of the Association of Space Explorers. You can go to our website and read about our planetary defense work over the last half a dozen years, mostly on the discussion of how to make decisions about eliminating the asteroid threat on an international level, fundamentally as important as the technology that we'll employ. So I'm interested in not only preventing future collisions, but also enabling us to use our exploration skills, our thinking skills, our adaptability, our flexibility in using these bodies to catapult us out into the rest of the solar system and to look back from an asteroid someday at the pale blue dot that we came from and realize that this is our destiny out there in space. So we've got to use the information that we gather about the asteroid population, searching for dangerous ones, to also identify exploration targets. And that enables us to send robot explorers out there. We've sent the Near-Shoemaker spacecraft to Eros. We've sent the Hayabusa spacecraft to Itokawa. And, there are future missions on the books like Hayabusa 2. And we've also got the NASA Syrus Rex mission from our University of Arizona friends that's going to go to a hazardous and very volatile rich asteroid. I was on a project last year with my friends from NASA Ames, and we had a concept for an asteroid lander called Amor. which would go to a triple asteroid system. Now, NASA didn't fund it this go-around, but we hope that this concept will have some legs, so to speak, and we'll get to fly in the future with, as a precursor for robotic exploration. So humans are going to need some robot scouts, and a series of them like this, to explore potential targets. And in the meantime, in parallel, for humans, we're developing systems that can take us beyond the orbit of the space station where I've been, and then out to deep space destinations. The moon. Not right now, we're not talking about the moon in the current administration, but it's certainly within the capability of a deep space craft like the Orion multipurpose crew vehicle. But if you build a vehicle that can go to the lunar vicinity, you can also go to nearby asteroids energetically. They're very close. In fact, sometimes easier to get to the asteroids than landing on the surface of the moon and coming back. Just a couple of weeks ago, NASA announced the new Space Launch System, a big rocket bigger than the Saturn V that Rusty flew on Apollo 9. Whether it gets built is entirely dependent on the President and Congress agreeing on how to fund it. Technically, it can be done, and we need a big system like this or a number of smaller, more capable rockets that can be assembled into a package in Earth orbit. This is the current NASA thinking about how to get to deep space. And this thing, in the end, should have 130 metric ton lift capability to low Earth orbit, with 20% more thrust than the liftoff thrust of the old Saturn V moon rocket. But again, whether it ever sits on a launch pad like that depends on the budget over the next 5 to 10 years, and I'll talk about that in a moment. Typical mission profile for reaching an asteroid that a rocket like that and the Orion spacecraft could enable is drawn in this plot, looking down on the sun and on the Earth in green, and a plot by my astrodynamicist friend Dan Adamo from Houston. So here you've got a mission in 2020 to the asteroid 2009 OS5. It's coming in red. As you can see, it comes quite close to the Earth here in this part of the orbit. We launch in March, and by midsummer, you've arrived in the Orion spacecraft at the asteroid when it's close to the Earth. You spend a couple of weeks in a typical mission like this exploring the surface of the asteroid like we saw in my initial slide. And then the asteroid goes on its way. You leave before it gets too far afield, and you head back and land back on the Earth in the green orbit. So it takes 6 months, which is well within our free-fall medical experience on the space station. It's probably okay to expose humans to deep space, galactic cosmic rays, and solar flare hazards for about 6 months, counting on good luck to avoid any fatal events during that time, and some shielding preparation on your spacecraft. So that's probably the kind of doable mission profile we're thinking of. And just to remind us of the exploration challenge ahead of us, here's the space station, here's the proposed Orion vehicle, and then this is Itokawa that we visited in 2005 with the Japanese Hayabusa spacecraft. So just this boulder on the limb of Itokawa is bigger than most parts of the space station, and certainly bigger than, in fact, this kind of a boulder would have caused the meteor crater over in Arizona had it struck the Earth. So participatory exploration, what does that mean to me? That means that the astronauts show up here someday, but they take along the rest of us. And when somebody actually floats up to an asteroid, like in the Lockheed Martin dual Orion concept for an asteroid mission, we take the public along. We're close enough, only 1 million or so, or maybe 5 million miles away from Earth, that the light time barrier isn't too great, so we can transmit almost in real time, high-definition video, and you can look over the shoulder of some human representatives on a body like this. And during that 2-week exploration phase, you can get right down into the nitty-gritty with the explorers. Now, we used to think of astronaut visits to an asteroid as being in these Orion spacecraft. Bare bones, about 4 or 5 years ago, we thought about cramming 2 people and all their supplies in one of these vehicles to go on a 6-month trip to an asteroid. It's probably too much to ask of any reasonable human beings in the room here tonight. Now NASA's thinking about reusing flight hardware from the space station and our other programs and our international partners to maybe put together a package that's bigger and roomier and enables the astronauts to have more comfort and more reduced risk of surviving the trip, reduced risk of a hazard that might prevent them from surviving the trip. We want them to survive the trip. So you have an Orion for getting back to Earth, but you also use space station modules like these that have been built and flown. We know they work. This is a Russian module from the space station program. There's a Soyuz attached as a backup reentry vehicle. And then even an orbiter airlock from the space shuttle has been employed to carry solar arrays and allow you to depart on a spacewalk. So maybe using these flight heritage modules, you can, in the next 5 to 10 years, assemble a package that can reach the lunar vicinity, or one of the Lagrange points, and then eventually go on to an asteroid without having to reinvent the entire wheel with the attendant expense. Now, when you get to an asteroid, and you have got 2 weeks to explore it and do some field geology, you want to pay attention to how you deal with the challenges of the asteroid. It's rotating on a period of probably several hours. You've got to get from your cruise vehicle. It's too big to land on the asteroid, so you've got to get over here to work. So do you have a jetpack on your spacesuit? That's what I thought would be the easy case just a couple of years ago. And then you would find yourself in placing an anchoring system and just clambering around like I did on the space station. And you do your field geology work that way, essentially exploring on your fingertips in this very low gravity body. But that's very fatiguing, and I can tell you that from experience. And if I'm going to get maximum return science-wise and resource-wise from this 2 weeks, I want to have better productivity than a spacesuit can give you with all its encumbrances and stiff gloves and shoulders and arms. So NASA, I think very wisely, has been thinking about adapting lunar rover-type vehicles that usually have wheels on the bottom, and then giving them a propulsion package and the ability to fly in space in free fall, and then putting a couple of people inside a space exploration vehicle. This is 2001, A Space Odyssey, which I watched as an 8th grader and was just stunned by. And maybe that'll actually come true in this version where you have manipulator arms to anchor you to the asteroid. You can work in shirt sleeves. You can go out there for 10 or 12 hours, take a lunch break while you're hanging on with a robot arm, and then go back to your field geology. And you tuck your samples into a bin on the vehicle and go back to the mothership. So a lot of advantages to working in your shirt sleeves, and this might be the way to go. And we should test this design on the space station in the next 5 years so that you show that you're moving towards this asteroid capability, but you're doing it in a way that is close to home and is really an extension of what we've done already. If you master those kinds of exploration challenges at the asteroid, you build the heavy lift launch vehicle, deep space, that's all Mars forward experience for getting here eventually, 20 or 30 years down the line. And I think as we move off into the asteroids that come close by and demonstrate the capability to not only move them from striking us, but getting humans moved out to the asteroids, you're taking steps to physical stepping stones, greater distances from Earth that get you the experience to get to Mars one day. But you're also taking advantage of the asteroids as knowledge stepping stones to extend our reach and experience so that we have the confidence and the ability to guarantee that some of the astronauts going to Mars eventually will make it home alive. And that risk reduction is all important in taking on this challenge in the future. What I like so much about the study this week that we're doing is that it sort of turns the asteroid problem inside out. Instead of sending humans first to an asteroid 5 million miles away, we're trying to think about bringing a small asteroid close to home where humans can go there with less risk at first before we stretch our space legs. Whether it all comes true or not depends on whether we have a budget that can support some of these developments technically. This is the federal budget divided into 100 squares. You can see that entitlement spending takes up more than half, Defense Department about 20%. Here's the net interest on the debt, and there's NASA with half of one square, about 0.6%. Unless our government and our policymakers can get together to expand that by just a little bit to maybe 6 or 0.7%, I don't think any of this is going to happen in the next 10 or 15 years. And the president's promise to go to an asteroid in 2025 is moot unless we can find a way to expand this little share of the pie with the commercial innovation that's going on to enable us to get out here. So I'd like to think that our study this week and some brainstorming by NASA in the next 5 years will see us find ways to make use of our existing experience and hardware and see us off to the asteroids by this 2025 date that we're shooting for. Looking forward to it myself. Thank you.
Thanks, Tom. And if I can interject a comment, I just, in my email tonight, I saw an announcement that not only is the NASA budget not likely to expand, but there are attacks on it going on right now in the preparations of next year's budget. And even this one corner of activity, which we do, which is so positive for the planet, is in danger of being shrunk. So I think Planetary Society members will hear from us and say we need to be engaged on this subject. I'm now very pleased to introduce Professor John Lewis. I've known John a long time. In fact, even once did a paper on Venus. No, actually, we did it on Earth, but we wrote about Venus. John is a professor of planetary science. We've been at the University of Arizona Lunar and Planetary Laboratory, but he's actually a cosmochemist who has taught at MIT, he's Princeton, Dartmouth, and the University of California, San Diego. He has done a lot of seminal work on the whole subject of what are asteroids good for. You heard the bad news from Rusty about what the danger is, but John has taken a more positive look and saying they're good for something, and I think the good for something has both a scientific aspect to it and an economic benefit to it, and we're going to hear from Professor John Lewis. Thanks.
This recent sequence of discoveries of near-Earth asteroids has really opened our eyes as to what's out there. And it's possible to look at these bodies both as a threat and as an opportunity. They surround us, they cross our orbit regularly. A number of them have passed between Earth and the Moon. If that's not close enough for you, we're going to have one asteroid pass through the geosynchronous satellite belt in the near future. This is going to be a very real experience for us, watching this bullet approach us and skim by. So we're very interested, for a multitude of reasons, in the outcome of the observations of that asteroid to see what its future path is going to be. I think the thing that attracted me to this subject originally was not the hazard aspect, although I certainly worked on that as well, but the fact that this near-Earth asteroid population is very diverse in composition. We have some 10,000 meteorites that we've analyzed in our laboratories here on Earth. These 10,000 meteorites represent fragments knocked off of approximately 50 different asteroid-like parent bodies by impacts with other small bodies. And what do we have among that population? Well, among those 10,000 meteorites, we have an enormous range of compositions. The majority of them are what's called primitive material that has never melted and differentiated, separated into layers according to density. Earth, of course, has. We have a core, a mantle, and a crust of different densities whose separation was facilitated by the melting of the Earth. But most asteroids have not melted and differentiated, and indeed most of the meteorites that fall on Earth are primitive material. They represent a kind of a cosmic sediment, rather uniform in structure, with a variety of different minerals in them. Some of them were formed under rather wet conditions. These meteorites are called carbonaceous. They are black in appearance, very low reflectivities. They contain up to 6% by weight of organic polymers. They contain up to 20% by weight of water. In fact, these meteorites, as they fall on Earth, looking like lake bottom sediments, have up to 40% by weight of easily extractable volatiles: hydrogen, carbon, nitrogen, oxygen, sulfur, and so on. This means that they are potential sources of large quantities of water, of hydrogen and oxygen from the electrolysis of water, of carbon compounds for space habitats, for agriculture in space, for sources of nitrogen, for the atmospheres in space habitats. So these volatile-rich meteorites make up a small percentage of the near-Earth population, but they are there, and they do fall on Earth. We have many samples of them in our collections, but they are weak material, quite weak. So weak that if I had a fragment of one that I could hold between my thumb and my finger, I could crush it just by squeezing it. Needless to say, when these objects enter Earth's atmosphere at high speeds, they have a tendency to crush and explode quite high above the ground. So we see fireballs from time to time whose spectra show the emission lines of large quantities of carbon and other carbon compounds. And we know that These things are available among the near-Earth asteroids. We see near-Earth asteroids that are that dark, and some of them show quite clearly traces of an absorption feature in their infrared spectrum at around 3 micrometers wavelength due to water. So these objects are of great interest to us because they can provide not only life support materials, but also hydrogen and oxygen and carbon compounds for propellants. So if we have any future in space at all, and I decided at the age of 5 that we did, please don't prove me wrong. Okay? I can remember when we had a future in space. All right? When we look at these volatile-rich asteroids, we are tempted to say, if we were out there, we could use them very profitably. In addition, the majority of the meteorites coming from the near-Earth asteroids are primitive, but not containing water and carbon compounds. They're dominated by basically 4 different minerals. The principal minerals are 2 iron magnesium silicates called olivine and pyroxene, plus metallic iron, which is really a native, natural stainless steel that makes up anywhere between 5 and 30% of the mass of those asteroids. And they also contain iron sulfide. So we have these nearby asteroids and the fragments from them ranging in composition from lake bottom mud to stainless steel. If we see an asteroid approaching Earth, it would be of great interest to us to know which it was. Because if it's a chunk of carbonaceous chondrite, it will explode high above the ground. And unless it's really huge, the blast effects won't do much to us here on the ground. On the other hand, if it's made out of stainless steel, that is an armor-piercing bullet, and that will pass right through our atmosphere and impact the ground at essentially the same velocity at which it hit the top of the atmosphere. In fact, in some cases higher, because the energy picked up in falling to Earth through the atmosphere more than compensates for the energy lost to friction by passing through the atmosphere. So we need to know what these bodies are made of. We need to know what orbits they follow. And we certainly need to have some idea about what to do with them. If we think of these bodies as potential resources, there are many resource uses in space that we can associate with these bodies. Propellants and life support materials I've mentioned, but what about all those metals? Well, they contain large quantities of native metals. Very little chemical energy needs to be expended in extracting those metals. A magnet will do it. The regolith of an asteroid is a powdered deposit. Run a magnet through it and you can extract the metals. So we can build large-scale structures in space out of those metals. And there are technologies for processing these native metal alloys and separating them into their components. Those components being iron, the main component, nickel, making up typically about 7% of the total mass of the metal, cobalt, making up about 1%, and platinum group metals, making up about 100 parts per million of the metal. The smallest known metallic asteroids contain more metal than has been mined on Earth in the entire history of the human race. The smallest known. If one of them were to hit Earth, it would penetrate the atmosphere as if it were a sheet of paper, and it would blast a sizable crater in the ground. We're talking here about a body which is over 1 kilometer in diameter. That body compares to the meteorite, the asteroid fragment that made Meteor Crater in Arizona, quite unfavorably from the point of view of people who live on Earth. It's about 10,000 times as massive, and it will hit with considerable force and explode under the ground surface. It'll penetrate right into the crust of the Earth before exploding. It'll produce a huge crater, many kilometers in diameter. Meteor Crater, on the other hand, is a few tenths of a mile in diameter, about 1 kilometer. So we need to know what they're made of. We need to know what paths they're following. And we need to think of uses for their materials, because if we use them up before they get to us and use us up, we're ahead of the game. One possible use for metals in those asteroids is to build large-scale space structures, such as space stations, habitats, and solar power satellites to capture sunlight, convert it into microwave power, beam it down to Earth, and provide our energy needs for the coming few billion years. Because that energy source will be good until the sun becomes unstable in its old age, and when the sun is facing retirement, it gets out of hand. Fortunately, we have a few billion years left before that happens. Are there any things in these asteroids worth bringing back to Earth? Well, yes. Two categories that I can identify. One is precious and strategic metals. The other category is energy. Energy delivered to Earth from space can be in the form of solar power beamed down from solar power satellites. It could even be in the form of helium-3 fusion fuel. I know some of my colleagues are firm believers in the prospect of mining helium-3 from the surface of the moon and using it to fuel fusion reactors here on Earth. If one can suspend one's belief a little bit, for example, knowing that we don't have fusion reactors yet, and knowing that there is 1 ton of helium-3 fuel for each 100 million tons of regolith on the moon. If you can suspend your belief on these matters, well, you can probably believe anything, but I frankly don't think that this is going to work economically. But I can define a couple of cheap experiments that would help us determine whether this is an economic possibility. These experiments have not been done. We don't know about the extraction of helium-3 from the lunar regolith. We don't know the best way to do it. We don't know too much about its distribution on the moon either. And if it's helium-3 you're after, the atmospheres of the giant planets have considerable concentrations of it. Just as an indication, the atmosphere of Uranus above the cloud tops has enough energy to power all of Earth at European, North American, Japanese standards of energy consumption for 10 to the 15th years. So there's plenty of resources out there. There's a shortage of perhaps motivation or desire. All right, I'm going to just sum up by giving you an overview of the asteroid potential of the near-Earth swarm. This will only take a couple of minutes, so please bear with me. We can determine what quantity of each element or each resource is needed to sustain one human life in a highly industrialized society. That material, that total material that we need to sustain society is called demandite. We can go through and compare the amount of iron and the amount of carbon, the amount of water, and so on, needed to sustain one human being. And then we can compare that to the known composition of the near-Earth asteroid swarm. Then we can ask a very simple question. Let's suppose we had a fully recycling society using the resources of the near-Earth asteroid swarm, powered solely by solar power, and indeed the only input is solar power. Right? How many people could you support? And the answer is we could support a population of 10 billion people indefinitely until the sun dies with those resources. However, the near-Earth asteroids are not an exhaustible resource. They're constantly replenished by recruitment from the asteroid belt. So the future may be brighter. Don't be depressed by that number. Most near-Earth asteroids come in near Earth, into the terrestrial planet region, and an aphelion go out into the asteroid belt. So once you establish any kind of a facility on a near-Earth asteroid, it serves as a traveling hotel and traveling gas station to take you out to the asteroid belt. There you can jump off, adjust your velocity to rendezvous with a near-Earth, with a belt asteroid, and suddenly you have access to a larger mass of material. How much mass? 1 million times as large as the total mass of the near-Earth asteroid swarm. There is no shortage of resources out there at all. So if you want to support a large population, at a high standard of living. We have resources inside the orbit of Jupiter capable of supporting 10 to the 16th people. And needless to say, we are not bringing that all back to Earth. Okay? So there's a potential out there for us getting out of the cradle, in the terminology of Konstantin Tsiolkovsky, and liberating ourselves from the bonds of Earth, to be poetical about it. And all of this, our very cradle, is threatened by the impact of these same bodies. So it's up to us to decide, is this merely a threat, or is this also an opportunity? If we make the correct decision, then we have a glorious future, not just for a few hundred years or a few thousand years, but we have billions of years of open track ahead of us. So when you think about the future of our space program, what is it worth to us to have access to space and to have the ability to go out there and manipulate and maneuver asteroids? Is this some far-out fantasy, or is it the key to an unlimited future? That question will be on the final.
No shortage of resources, no shortage of ideas. Very nice, John. Thank you. And if you think your mind has been expanded thus far, just wait till you hear the next speaker. I'm very pleased to introduce a man who needs no introduction, but I'll introduce him anyway. Bill Nye, the Science Guy, and I see a lot of young people here tonight, which is one of the reasons I'm very excited, very proud, and very happy that Bill Nye has succeeded me as executive director of the Planetary Society. Succeeded in both senses of the word, following me and also bringing it to new successes for a whole new generation. Bill is a well-known science educator, a longtime television personality who has influenced so many people about the joys of science and inspired so many people of Earth. And this is our job at the Planetary Society, to inspire the people of Earth to explore new worlds. And I'm very glad that Bill is joining with us. Bill.
Ladies and gentlemen, boys and girls, kids of all ages, it's great to see you all. Thanks for coming. I'm just going to show you what we at the Planetary Society, the world's largest non-governmental space organization, are doing, what we are doing about these objects. Because they're a source of great fascination, of course. And as Rusty Schweickart pointed out, if you're going to be a successful civilization with any sort of reasonable number of centuries, you're going to have to pass this test. So this, okay, wait. No, really. Okay, no, this is going to do it. No, this is it. I'm not kidding.
You know what? I'm going to give Rusty an A+, and Tom, I'm going to work it in.
The end.
No, it's not your fault. It's. I'm sure it's me. So.
No.
We won't blame anybody but me. So.
These pictures are just going to change your lives.
There you go.
So this is an artist's rendering that we like. If something got this close, the expression that I like is "ah!" This would be really bad. We can't let things get this close. And for those of you, how many people are not members of the Planetary Society for some reason? Well, we're going to work on that, my young friends. But how many of those same people saw the original Star Trek? Sure, right? Even then, in 1966, they had Miramani and the Fabrini, and they had an asteroid deflector beam, just like you have in your car. And they addressed this problem, but if you remember, there were some issues with that technology being lost. And so we can't let that happen. This would be some people taking, I guess, the Orion spacecraft, landing on an asteroid, and then we'll see how it goes in transferring from one piece of software to the other. Yeah, well, then I guess you turn on the rocket engine and just nudge the thing out of the way. This would be a really hard problem, but it's one you just can't help but wonder about. Like, could you just nudge it out of the way? This is the Syrus Rex mission, and I'm proud to say the Planetary Society is the outreach, education public outreach entity for Osiris Rex. And the idea is to characterize asteroids. So this will be a spacecraft that will go up, scrape up a little bit of asteroid, and bring it back to the Earth. And this will be take several years, but this is a classic example of, you say, well, what are you guys going to learn by scraping up a piece of asteroid and bringing it back to the Earth? We don't know. That's why we're going to try it. So if we could do it robotically, it would be we'd learn a great deal about doing it with humans. So this mission's coming up in a few years, and I just wanted to say Osiris Rex is an acronym. And look, I consider myself a creative person. I've written a lot. That is a tortured acronym. That is a long way around to get to this king. So and of course, charming thing, the X is lowercase, because the last one's experiment. Yeah. All right. But this will be a very cool mission where humans learn more about what I love to call our place in space. So we are discovering in my lifetime, first of all, I remember very well when people suggested that the ancient dinosaurs were killed by their brains. Their brains were too small and they were stupid. And they starved to death. Okay, well, in my lifetime, yeah, exactly. So in my lifetime, it's been shown, if you're looking for a good theory about what killed the ancient dinosaurs, it's probably an asteroid or collection of space stuff that took them out. And so there will be discoveries in your lifetime, I see young people here, that will change the world in the same way. And this is the excitement of space exploration, is that, as I always say, it really brings out the best in us. It brings out the best in people. And so we want to find a way in our lifetime to nudge one of these things off course. So the Planetary Society, one of the little things we fund is a study with the mirror bees. And the word bee is just charming because they kind of resemble a swarm of bees. And these would be mirrors in space around an asteroid. You'd shine enough bright sunlight on it to volatilize the surface, cook it to the point where it boiled off, and then the reaction of that gas or material being ejected from the asteroid would nudge it off course. But once again, my friends, this will only work if you get there early. You can't show up late. You got to get there a decade or so early. But wouldn't that just be cool? And by the way, no nuclear propulsion required. No controversy about sending radioactive material into space. This would be probably sent by conventional rockets, probably deployed in a way not unlike we use cell phones with distributed computing among the spacecraft. They would get themselves organized, and they would cook the asteroid and just give it a little nudge off course. It'd be a very cool thing. And you're saying, well, when are you guys going to build these? Well, we're working on it. All right. If an asteroid or if an object is identified soon enough, I'm sure we will all want to rev this up. And this is the kind of thing, if you want to, as I say, if you like to worry about things, you're living at a great time. We have a debt crisis like no one's ever seen, an economic crisis around the world. We have human immunodeficiency virus. We have the potential with world travel of any really deadly or dangerous disease traveling around the world in less than a day. We have by Halloween, when I went to the World's Fair in 1965. My father and I just saw the world population change to 3 billion, from 299,999,999 to 3 billion. Well, by Halloween, everybody, we should pass through 7 billion. 7 billion people. And they're going to want stuff. And so we have to find ways to do more with less. And part of the problem with modern natural disasters, earthquakes and tsunamis and stuff, we have more and more people living near the coasts. And if you are an asteroid and you're going to hit the Earth, you're probably going to land in the ocean. and you're going to take out even more people. So this could be something that just will wipe out your concerns about debts and diseases, and this could just overpower the whole thing. So if you like to worry about things, join us. Join the Planetary Society, because what I like to say, if you join the Planetary Society, we don't just talk about, we are doing things. We do stuff. So we're funding the bee people who are largely in Scotland. Is anybody from Scotland? It was fascinating. I think if you wake a Scottish person up in the middle of the night, they talk like we do, you know. But they're so focused. They're so focused on scaring us all. Also at the Planetary Society, this is an old idea, and Dr. Friedman, whom I have succeeded as executive director, wrote a textbook about this sort of thing in 1975, at the height of the disco era. Well, everybody was rocking out at the disco, pumping out the bass, Studio 54. Lou was a proponent of the idea of pushing a spacecraft through space with sunlight. And then those of you who are normal people out there who are not involved in this business full-time, civilians, sunlight? That's crazy. I thought photons had no mass. How can they possibly have momentum? That's madness. And your point would be very well taken. But this is a little thing you can do. We do this with science teachers all the time. Everybody loves E equals mc squared. Who doesn't love that? Nothing but fun. Now, divide both sides by the speed of light. Just takes a second. And you'll get an expression, mc, which resembles mv, which is like momentum. So if you have Planck's constant and you believe in quanta and stuff, you can show that light has momentum. Now this is three orders of magnitude bigger than the solar wind. It's not the solar wind that pushes these spacecraft. It's sunlight. It's quite a remarkable thing. So our solar sail, we hope will launch by December of 2012. Our problem is we have to get above, just as an aside, we have to get above the atmosphere. Even when you're on the International Space Station, you're flying in the space shuttle, there's atmospheric drag. We have to get up above 500 kilometers, above 300 miles. You got to get up to like 800 kilometers, 840 kilometers, 500 nautical miles. And so we're waiting for a ride, as the saying goes. And our understanding, maybe our best shot is with an OGA. We love acronyms. That's an other government agency. And so we're hoping, because apparently a lot of spy satellites go to these medium orbits. I make no promises, but we certainly hope by the end of next year we will fly. So what does this have to do with asteroids? So here's Eros. Well, actually, it's a picture of Eros. If we had the asteroid Eros here, I don't think it would even fit in this room, to tell you the truth. Yeah. It's a couple miles across. So it's a little bit reflective. Yeah, that's a joke if I'm going too fast. It's a little bit reflective, but what you might be able to do is wrap it with shiny saran wrap, and then you'd get a little delta V. And this might work. This might work even if the thing is rotating. Like if you could get it wrapped, even if it's turning its back to you and stuff, it still might work. So anyway, it's okay, I make no promises, but it's something to investigate. Then this is a picture compiled by Emily Lockdewall. I know many of you who are members are fans of Emily. She does our blog. She's very insightful. So these are asteroids that our spacecraft have visited. And she doesn't have Vesta on there yet, which would overwhelm the thing. But you see there's a lot of them, and they're very irregularly shaped. So when you go to think about asteroids, it's just interesting to note that they don't have enough gravity on their own really to form balls. So when you go to give them a push, it's one more thing you got to take into account. And I leave you with this because the Planetary Society funds the Shoemaker NEO grants. These are near-Earth objects. And we have people, observers in the southern hemisphere and other parts of the world that keep an eye on near-Earth objects. And we fund them. And so the people who worry, they help us keep these people in business. And we're going to go look at Syrus Rex. We're going to fly a solar sail. We keep funding the Mirror Bees investigation, and we are doing something about what I like to call the only natural disaster that humans can prevent. So join us and let us, dare I say it, change the world. Thank you.
If the panelists will come up to the table, we'll get into a question and answer session, and we'll have an opportunity. I'm going to start out myself with a question for the panel, and then really ask the audience to get engaged. If the audience has no questions at all, you'll go home early, and if you have some questions, you'll go home a little later. So I'd like to start this discussion by worrying about something. Bill says we all worry. We talked about asteroid deflection and the importance of considering this. But Carl Sagan actually brought up the worry that if we can actually move asteroids, doesn't that give us the capability to actually move them and create a weapon? We can move that and end up targeting the Earth. And so that the idea that we are now engaging in this technology that we might use for advantage could just as equally perhaps be used for disadvantage. And is that a worry we should consider? And if it is, what should we do about it? So let me see if any panelists could address this. Rusty.
Yeah, Lou, Carl and Steve Ostro and a number of other people wrote about this in the early 90s, back in the nuclear winter days, and it was really written as much for sort of political purposes as technical. But the whole idea of if you can deflect an asteroid away from the Earth, you can therefore deflect one toward the Earth and have it hit Baghdad or whatever, your favorite enemy. It's really not an issue, and the most obvious reason it's not an issue is that if you look at the frequency with which an asteroid that can really do damage on the ground hits the Earth, that's about once every 200 to 300 years. So if you have an asteroid come by the Earth which threatens the Earth once every 300 years, then that would also say that you're going to have an opportunity once every 200 or 300 years to go up and have a weapon to hit Baghdad. Of course, the problem is that by that time, the Zambian space program is the world's premier space program, and Baghdad is a buddy of yours. It's a lousy weapon because you get a chance to use one once every several hundred years, and even then, you can only deflect it to hit someplace along sort of an arbitrary line across the Earth. You can't move it arbitrarily.
So it might only be going over Alaska and Canada, and
right?
We want to hit those.
Yeah. So you have to make an instant enemy of Canadians so you can hit them with an asteroid. So it's not really an issue, but the thing that is important about it is that the public perception of asteroids is pretty scary. Can be pretty scary, thanks to our good friends from Hollywood with Armageddon and Deep Impact and a few things. But we are, as we move forward with this whole field of asteroids and especially planetary defense, going to be facing the fact that it is something which the press and the general media misunderstand, don't really understand the dynamics, and there's going to be a lot of scare stuff. It's already out there. It's going to get worse, and that is going to be a very serious challenge that we, on the technical side, will have to deal with.
Any other comments?
Well, just as far as a weapon, I just remind everybody that that space is already pretty weaponized. There are a lot of weapons in space, and the global positioning system that we all know and love really was designed to guide weapons. So using an asteroid as a weapon is sort of kind of coming late to the party. It does show you, though, as Rusty says, it really gets to your deepest fears. I remember very well, when I was young, people referring to the ultimate high ground of space. This is like the bad guys were going to get in space and shoot down But this is not bad guys. This is Mother Nature that would be shooting down.
Okay, and I guess I can also take heart. I'll just add to Rusty's comment by saying I also take heart that, unfortunately, in a way, we haven't been able to get. Not only have we not been able to get the government, interested enough in this important topic, but we certainly haven't gotten the military interested in it, and so therefore it's probably not of interest as a weapon, given their reaction to the situation. I'd like to ask another question. One of the great honors I had in my life was speaking to the organization that Rusty and Tom are principals at, the Association of Space Explorers, which is, I forgot how many, but over 400 astronauts and cosmonauts, the people who have flown in space. And I think it's, we at the Planetary Society have done a number of projects with the Association of Space Explorers, including cooperating on the questions here. So I guess I wanted to give both Tom and Rusty a chance to comment on why have the astronauts and cosmonauts who are heroes of their countries and done such remarkable things, why are they getting into this problem? Why have they chosen this to work on?
One of the charter goals or objectives of the ASE is to protect the environment and expand our understanding of the environment of our planet and protect it in the future. From the vantage point of space, that's a superb place to study and then protect our Earth. So obviously a natural hazard like an asteroid impact is one that falls under that charter objective of our organization. And couple that with the fact that we're spread all over the globe, the cosmonauts and the American astronaut corps most numerous, but a lot of other international partners have joined us in space. So we've got representatives in all of these countries that have flown in space who can have the ear of policymakers. And so it's a natural thing, I think, for our organization to talk about this natural hazard, talk about how we can spread the word to the public about what can be done. As Rusty illustrated, a lot of the technology is already in hand. And with just a little organizational planning on the ground and some technical demonstrations to come in space, we can actually get a handle on these objects and prevent them. So the ASE, I think, is in a good place to not only nudge the discussions forward, but also to keep reminding people on a global basis how this can impact us, quite literally, and then prevent that from happening.
The other component of it is that, in some sense, you can look at the whole issue of planetary defense as comprised of three components. One is early warning. You got to find them and know it's coming at you. There's obviously nothing you can do. So early warning is one component. That's technical. Second one is something's coming at you. You got to be able to do something. That's deflection. That's another technical challenge, and we're kind of wrestling with that this week here at the Keck Institute. The third issue, however, is not so obvious to people, and that is that somebody's got to make the decision to actually mount a deflection and do it. And that is a geopolitical decision. And that is not technical, but it is the toughest problem of all, because you've got to get international cooperative decision-making. And to imagine bringing the world community together to make a collective decision to protect life somewhere is a big order, especially when the decision is you got to spend the world. Somehow, somebody's got to write a check for $500 million or thereabouts, maybe $1 billion, to launch a spacecraft or several spacecraft to this thing, with the probability being only 1 in 100 that, in fact, it really is going to hit the Earth. Because you're not going to know at the time that you have to act that it's going to hit the Earth. You have to act early, and therefore you have to make that tough decision before you know whether there really is an accident coming.
And so,
if you wait to make until you know, it's too late to act. So,
and is it possible you'll make it worse?
Only if you really screw up badly. You can't say never, right? But I mean, that's the least of the worries. The likelihood is we're going to end up with a big international debate until the day it hits. Frankly, that's the most likely scenario.
Bill, they used to teach us in astronaut school that you can always make a bad situation worse. So don't do anything is the right strategy most of the time.
Okay, I'd like to open this up to the audience. We have a large audience here, and if there are any questions, please raise your hand. Let me try to recognize you, and speak loud because you won't have a microphone. Do I see? Yes, right in the middle here.
Well, sir, why would that be so? Why wouldn't we act unilaterally in something like a $500 million project? That's not that big.
Okay.
The question was, why wouldn't we act unilaterally? Excuse me, Rusty. The question was, why wouldn't we act unilaterally and just do it, even if it's
And
only
we,
a
you mean
$500?
the U.S., right?
Yeah, if it's only a $500 million project. Well, maybe not. Maybe he's Chinese, and he's asking, why wouldn't we Chinese act unilaterally?
Number one, you can obviously not rule out unilateral action. I mean, you can't. There's no way to rule it out. The Chinese may just decide, screw, we don't care about the damn debate, we're going to do something, right? Okay, but just picture this. You got a line across the Earth. Let's just say it goes across the North Atlantic. On the eastern end, it goes across Europe and Russia. On the western end, it goes across the United States and out into the Pacific, okay? Goes all the way across the world. Let's say that the asteroid, which is going to hit along that line somewhere, but we don't know where, right? Suppose that in reality it's going to hit in the middle of the Atlantic, of the North Atlantic. Okay, now there are two choices that you've got with that asteroid, no matter what country you're from, all right? Physics dictates that when you deflect that asteroid, you either deflect it to the east and off the leading edge of the Earth, or you deflect it to the west, in that instance, off the trailing edge of the Earth. You can't do it any other way. You've got to go along that line. That's the only way physics lets you do it. So the Russians and the Europeans say, hey, take it across the United States. They have space programs. The United States says, take it to the east, across Europe and Russia. If something goes wrong in the middle of the deflection process,
Oops.
You now have a new impact point somewhere else. That's why this geopolitical issue is very, very sticky. We've got to have agreement between nations, and especially the spacefaring nations who would have to take the action, that they will coordinate their action and they will not act, are we going to race the Russians up to the asteroid to push it at them instead of them pushing it? I mean, that makes no sense at all. So that's the reason.
Okay, any other questions? Or yeah, here in front.
Well, in response to what he just said,
Speak loudly.
Speak so Lou can hear you. And he repeats.
in response to what he just said, why can't we push the asteroid out of plane? Why can't we just push it faster?
So, question is why limit yourself to just 2 dimensions? Why not just give it a boost in another direction that would be less?
More north and south,
yeah.
west, east, and west.
Give us more options.
Yeah. This is straightforward orbital mechanics. Unfortunately, that's not part of the general, intuition of society. But I can tell you the result. That is, if I push something other than along the velocity, in other words, if I do anything other than speed up or slow down the asteroid, okay, it has almost no effect. It does have a small effect, but it's cyclic. And therefore, you don't have any cumulative payback from the investment of energy that you spent. If I change the velocity of it by speeding it up or slowing it down, then each orbit thereafter, it accumulates an effect. So the cumulative effect of a deflection is thousands of times greater in terms of the effect of changing the orbit of that asteroid than thrusting or then moving it, changing the velocity any direction perpendicular to that. But we have to go into big equations for you to
a smaller
understand
orbit goes faster, a bigger orbit goes slower. That's
right. I mean, the diagram I showed at first is the whole secret. You got an intersection, and what you want to do if the asteroid and the Earth are going to get in that intersection at the same time is you want to change the arrival time of the asteroid. You want to make it arrive late, or you want it to arrive early. And the way you do that is basically, as Bill is implying, by changing the size of the orbit. You change the size of the orbit by either speeding it up or slowing it down slightly. You don't have to do it much. 1/10,000th of a mile an hour is all you got to change the velocity. But on the other hand, since it weighs a few billion tons, that's a big change.
So I have a bias toward younger people who might want to ask a question. I see someone here in the front row I think is getting ready to ask a question. But if, please, any other questions? See someone there, and yeah, go ahead. Yes.
Okay. So you're saying that to move such an asteroid, everything has to be extremely precise. However, if there is something that goes wrong, the astronauts have to return, or something extremely bad happens, do we have, and it's basically too late, do we have a type of plan B, or at least a way of dealing with the public, of telling them that there is a chance that a space object is going to collide with the Earth and kill 4 billion people?
So the question is, things can go wrong, and even if they don't go wrong, there's a chance of asteroid collision killing a lot of people and having huge effects. Do we have a plan to inform and engage the public on this?
Well, I hope everybody's already pretty scared once the thing's discovered. And then what if it really is 500 million a rocket? Then I hope we would agree to launch several rockets, just for redundancy.
Yeah, Bill, but you're actually called upon quite a lot by news media and even by the president to comment on things that explain science to people. So if the president calls you and says, just had an emergency meeting with leaders around the world, and an asteroid is headed this way, and we have to take a risky action which actually might still result in many deaths, would you go on television and explain it to the public? How would you do that?
Sure, Lou. Hi. So we're in greetings. My name's Bill. We're in a situation where at least 2 billion people are going to die, and every economic thing you can possibly think of will never, ever work again. Or we could launch this rocket and take a shot. What do you think? I mean, the scale of it, the scale of this, when the meteorite or the object or the group of objects that took out the ancient dinosaurs, the dust from that impact went about halfway to the moon. And so these calculations are really compelling. It's at first hard to believe that just one object could create that much havoc. But if you have an impact so strong, you're taking a measurable fraction of the Earth's crust and throwing it halfway to the moon. That is a big impact. And so the scale of it really is astonishing. In the case of Apophis, however, which my understanding is is anybody Greek? Apophis was the Greek god of anxiety. Is that right? The Greek god of worry?
Paul, correct him?
In the end. Oh. The end. The end of everything. That's a great name. It's probably, if you're a god and you have that gig, I guess you're just kind of waiting for your moment. Yeah. So apparently that one would hit in the middle of the Pacific Ocean, and then you would create tsunamis that are of astonishing magnitude, and some humans would be largely unaffected. Is that right?
Oh, a lot.
Yeah.
But there would be a lot that would be, yeah.
Yeah, but if you destroy the economies of the Pacific Rim and kill, pick a number, a couple billion people, that's going to have an effect on everybody in the whole world for the foreseeable future. So that's a good question, and to me it shows the importance of this. That although we don't know of an object right now, we know that there have been a lot of objects in, every 2 or 3 centuries.
There are some living systems which are far more sensitive than even we humans, who are very, very sensitive, by the way, and vulnerable. For example, civilization, the world economy, culture. Those are living things which we have created, but they are far more vulnerable to impact than the extinction of humanity. So it's going to take something. I was just looking at it. Itokawa, this is not the greatest lighting at the moment, but if you remember looking at all these different asteroids, the smallest one up there, is Itokawa. It's a dot on this diagram of asteroids, and that would be a civilization ender if Itokawa hit. That's a 500-meter long. It's probably, if you rolled it up in a spherical ball, it'd be 350 or so. But that's probably a civilization ender, not a species ender, but a civilization ender. So we literally have a million things smaller than that can do serious damage on the ground. The smallest ones we worry about are about 30 meters in diameter or so. There are about 1 million of those, more or less, and those are about, for each impact, would be about 350 Hiroshima nuclear bombs going off at one time.
But what's cool is we can do something about it, we think.
Yeah, we can stop it. We can end it.
Yeah, that's what's cool.
That's.
So I'm now going to give preference to somebody who has a happy question. Okay, way in the back.
It's happy. So bad.
So, Rusty, I think you mentioned that preventing an asteroid hitting the Earth using kinetic impact. And along those lines, back in 1998, I saw a great film starring Bruce Willis. They drilled into it and stuck a nuclear bomb in it. Is something like that a possibility?
I can't appreciate your taste in film. You don't need old astronauts to go up and save the world. Everything that we're talking about here, not Tom's stuff. I mean, what Tom was talking about was the human missions to asteroids and related to asteroids. But in terms of planetary defense, this is all robotic, and you really don't want people around. That makes a mess, whether they're Bruce Willis or Tom Jones.
The other thing is, you guys, momentum is conserved or what have you. If you blow it up, then the whole giant spray of rocks is coming at the Earth instead of one. So only a couple of cases is it really a good idea to blow it up. Is that accurate?
Yeah. The international debate that I talked about earlier, which is going to go right up to the moment of impact, would be far more intense if what you're proposing is to use a nuclear explosion. At the same time, if what you care about is the technical issue, and Tom and I have dealt with this for years in the United Nations, if what you're talking about is technically getting the job done, forget the geopolitics. If you're talking about technically getting it done, there is a very small possibility that we could be challenged the first time by an object too large to use a kinetic impact, and the only thing that would work would be a nuclear explosion. So we always state very carefully that the potential use of nuclear explosives for deflection cannot currently be ruled out, but it is an extremely low probability that they would be needed. And I'll tell you, the real challenge which is going to force them to be needed, it's not the size of the object, it is the length of the debate. Because what's going to happen is the more gentle green techniques for deflecting asteroids disappear one at a time as you get closer and closer to the impact. So if the debate keeps right on going, which it will, then the world community who hates nukes in space as an idea is going to force nukes in space or eliminate civilization. There you go. Thanks.
That was the happy
United
question.
Nations.
Now I'm going.
That's
All
the
right.
happy news.
Yeah, okay. I only have time for one or two more right here.
Yeah, I've got two, so I hope we don't quite back.
Well, I don't know. You maybe. Let's see how good the first one is first.
One for Tom, one for Rusty, one for Tom. As you said, they would use space station components. Would these be components that are currently part of the space station, or would they be something like demonstration test model parts that were on the Earth, identical to the ones that were launched, and would be used separately?
Both, and I think that NASA should and its partners should consider both options. You've got assembly lines that can build the hulls of modules already in operation, and cargo vehicles are being built like that today to go to the station. Those can be churned out as new articles to be incorporated into a NEO spacecraft. But the space station has components that will age and succumb to old age at varying rates, and when you get to 2025 or so, parts of the station will be kaput and no longer sustainable. parts will be humming
German
along.
Parts, right?
Parts will be humming along just fine. And so one of the smart things that NASA could do, rather than dump the entire thing into the Pacific Ocean with its partners, is salvage the good parts and boost them up to a place where they can be injected off to an asteroid trajectory. And I think that's got much better public relations value than just dumping the whole complex into the Pacific. So let's be smart about this and use the experience and the hardware and the most important, the expensive testing and development that's been done already, and make this a more affordable enterprise.
Okay, last question.
My experience with the public perception of nuclear is based largely on irrational hysteria. What are the prospects for using nuclear propulsion? For example, these things like the Nerva rocket that was so fantastically successful in the 60s and then abandoned for moving asteroids.
Yeah, nuclear propulsion would be a great thing for us to tackle, and
the political will to do it.
That's what's lacking, and the technology was almost flight ready in 1969 or 1970, and we put all that on the shelf. So it's possible to launch nuclear components inactive, safe, assemble them in space far from anybody down here, and then I think this would be a great way to get ourselves to Mars and other destinations someday. And you would prove out or test run those nuclear engines, nuclear thermal propulsion specifically, and then maybe nuclear electric on the way to an asteroid.
The terrible thing is that we've lost basically the whole human resource knowledgeable about space nuclear technology, and that we're talking about a couple of decades to really get it up and running again, even if there's a determined effort to do it, and that's a problem.
Also, for the Planetary Society, we advocated for the restarting of the plutonium-238 program. So plutonium-238 is not the weapons stuff. It's the stuff used to make these radiothermoelectric generators, the batteries. And it's this thing, this tug-of-war between National Aeronautics Space Administration, NASA, and the Department of Energy. So if you want to support just that level of deep space exploration, that's another thing we work on. It's a niche political issue.
Advanced propulsion technologies were once a subject of investment by governments around the world. And it's probably sobering to realize that American investment or research in advanced propulsion technologies peaked in the year 1964.
So it is sobering.
Well, it's sobering, but everybody, with all due respect to everybody, going to the moon I just remind everybody, the former Soviet Union made the first put the first cameras on the moon. They put they had the first soft landing on the moon. The first sample return. The first moon rocks came back by robot. But none of that mattered till people got there. Then everybody went crazy. But after that was accomplished, then the Soviet Union just kind of went out of business. And it really was a result of the Cold War. And keep it in perspective. In 2010 dollars, to put 12 people on the moon cost $151 billion in 2010 dollars. The interstate highway system, which is a very large thing and is still in use, the federal portion cost, if I can use the expression, only $114 billion. So if somebody's willing to invest 1 1/3 or 1 1/2 interstate highway systems, you can accomplish astonishing things. But what motivated you to do that? And what motivated the United States to do that generally was this perception that competing with this other government. So without that drive, the motivation for doing it is not as clear. However, if it turns out there's an object that's going to end civilization for all time, we hope we could all get together as a species and do something about it. If we found an object, we'll see if we don't rev up nuclear propulsion.
I spent a year several years ago as a visiting professor at Tsinghua University in Beijing. I got to know many prominent Chinese space scientists. In fact, I'm still a frequent commentator on China Central Television for space launches there. And it's very interesting to get their slant on space. They have never once expressed to me the desire to lead the world in space. They have frequently expressed a desire to catch up with the West. They deny that they are engaged in a space race, and I believe them, although there's a slight twist on that, which I think is they are indeed in a race with India right now. There's a large a pocket of expertise developing in China and in India and in, of course, much more established in Europe and Japan. There's a lot of expertise out there around the world to address these truly global problems. And I think it would be, although keeping the option of unilateral action open is wise for the reasons of self-preservation, there's a lot of talent out there, a lot of interest, a lot of potential investment. And I think it would be a shame for us to pull our heads in and think of this as being only our problem.
Okay, I do have to end the formal part of the evening. I strove mightily to keep lots of upbeat questions. I'm going to just close by saying that one of the upbeat things that really came through this evening was the great amount of human ingenuity and ideas that have been expressed here, and I think we all want to thank the panel very much for doing that this evening. I also want to thank the audience, great participation and great attention to this. Thank especially the audience who were outside and had to watch on the monitors out there, and we invite them to come in and hope in the few minutes we have remaining here you get a chance to see the panelists and greet people, and thank everybody very much for attending. Good evening.